Today we're going to take a look at section 1.3, evaluating limits analytically. Up to this point, we've been evaluating limits by looking at tables and looking at graphs. And while that's usually pretty good, it can lead to some issues. First off, computer software is good but not perfect, and sometimes graphs can be misleading. Secondly, sometimes the answers come out to be irrational numbers, or maybe rational numbers, but they're not particularly nice rational numbers, and you need a more accurate answer than just a decimal approximation. So what we're going to learn in this section is how to evaluate limits analytically, how to get the exact answers. Alright, so this chapter begins with a whole bunch of theorems. So I'm not going to write them all down. You can see them here in your book. I'm on page 59. Limit as x goes to c of b is b. If your function is just a constant, your limit is always b. If your function is just the letter x, you can take the number and plug it in. If your function is x to a power, you can just take the number and plug it in. And that's going to be kind of a common theme here. So that's a lot of what this next theorem says, properties of limits. Basically, what you have in this theorem and the next one, limits of polynomial and rational functions, the limit of functions involving a radical, the limit of a composition of functions, and finally limits of trig functions. Basically, what all these theorems combined go to say is that if you can go ahead and plug the number in and you don't end up with an error like a division by zero, go ahead and plug the number in and that's your answer. Alright, so let's look at some real simple problems here. For example, the limit as x goes to 3 of x squared. Well, what those theorems just said a minute ago is go ahead and plug in 3. 3 squared is 9. Simple as that. Limit as x goes to negative 2 of 2x squared plus 4x plus 1. Basically, one of those theorems said when you have a polynomial, you just go ahead and you plug the number in. So that's going to be 2 times 4 minus 8 plus 1. That's 1. Okay. Problem C. You get to do problem C for homework, and you'll turn this in to me on Monday. Part D. Pretty much the same thing happens with trig functions. This one says take the limit as x goes to 5 pi over 6 of sine x. Well, I know that sine x is defined everywhere, so I can go ahead and I can plug in 5 pi over 6. Now it would be nice if I could do a little bit better than that. Let's see. 5 pi over 6, that's a little bit smaller than pi, because 6 pi over 6 would be pi. So 5 pi over 6 is in quadrant 2. And I know that sine happens to be positive in quadrant 2. So this is the same as sine of pi over 6. And of course, that's one of the facts I've memorized. That one happens to be 1/2. Alright, once again, part E. There's a problem for you to try. Okay, so the crux of this section is what happens when the problems aren't so easy. For example, let's look at 2a. When I try to plug 0 in here, I notice that I get 0 on top. I also get 0 on bottom. And we know, at least we better know, that 0 over 0 is undefined. However, remember what we're talking about with a limit. With a limit, we really mean what's happening when x gets really, really, really close to 0, not necessarily exactly equal to 0. So while I cannot plug 0 into this function, I can plug numbers in that are really, really, really close to 0, and maybe I will converge to something. Alright, so here's the moral of the story, what we're going to do. When you get limits that are in the form of 0 over 0, like this one is, you have to do some algebra or possibly some trigonometry. You need to simplify. So we're going to rewrite this. This is the limit as x approaches 0, And I notice for this one that I can factor the top. I can take an x out. I can write that as x over x plus 3, and then I have that x on bottom. And then a wonderful thing happens. The wonderful thing that happens is those x's cancel out. And I now have the limit as x goes to 0 of x plus 3. And now I have a function where I can plug 0 in. When I plug 0 in, I get 0 plus 3, which is 3. Okay, so this is another one of our theorems in our book. Right here, theorem that I used, functions that agree at all but one point. And basically it says, if two functions are exactly the same, except for being able to plug the number c in, then they're going to have the same limit as x goes to c. And that's exactly what I did here. X squared plus 3x over x and the function x plus 3 are exactly the same function except when x equals 0. And so what I was able to do is I was able to factor and reduce. Alright, so let's try another one here. Okay, so we have the limit as x goes to -3 of x squared plus x minus 6 over x squared minus 9. If I'm doing this problem on a quiz or a test or a homework or wherever, the first thing I'm going to do is I'm going to try to take the number 3 and just plug it in. When I plug in the number -3, I get 9 minus 3 minus 6, that's 0. Divided by 9 minus 9, that's 0. I recognize that this is in the form 0 over 0. When I'm in the form 0 over 0, I need to factor and reduce. So this is the limit as x goes to -3. I factor the top. The top can factor as, looks like x plus 3, x minus 2, and I can factor the bottom. That's x plus 3, x minus 3. I now notice a good thing happens. My fraction reduces. This becomes a limit as x goes to -3 of x minus 2 over x minus 3. I can now plug in the number -3. -3 minus 2 is -5. -3 minus 3 is -6. So my final answer is 5, 6. Okay, now something I want you to notice. Not only is it important in math to get the right answer, it's also important in math to write the right symbols. So something that I see students do a lot, and something that when you do it, you will lose credit. You will lose credit for this. They will write limit as x approaches -3 of x squared plus x minus 6 over x squared minus 9 equals x plus 3 times x minus 2 over x plus 3 times x minus 3. You will lose credit for writing that. Oops, let me slide it over so you can see it. Okay? Notice when I did my problem, the notation I used. I wrote the limit symbol each and every time until I was able to get to the point where I was actually able to plug the number in. And notice I did that on the previous problem too. I wrote the limit symbol each and every time until I plugged in the number 0. The issue with this is these things are not equal. This thing on the left is a number. This thing turns out to be the number 5, 6, where this thing on the right is a function. So you need to write this limit symbol each and every time until you get to the point where you plug the number in and all you have left is a number. Okay? So, keeping that in mind, you get to do problem C. Alright. Problem D. Again, if I'm attacking problem D, I try to take the number 3 and plug it in. When I plug 3 in, I get 3 plus 1, that's 4. Square root of 4 is 2. 2 minus 2 is 0. 3 minus 3 is 0. I get 0 over 0. Okay, but this is a different situation. This time I can't factor and reduce. But we do have to use a different process in order to reduce. And the process this time, when you have a problem with square roots involved, is called rationalizing. In this case, the square root is on top, So I have to rationalize the numerator. And what that means, to rationalize the numerator, it means to multiply by the conjugate. Fancy words for saying multiply by square root of x plus 1 plus 2. The conjugate simply means change the sign in the middle. And of course, if I do that on top, I have to do that on bottom. Alright, so that leaves me with the limit as x goes to 3, writing that limit symbol each and every time, of, alright, on the top, I'm going to go ahead and multiply it out. I take square root of x plus 1 times square root of x plus 1. Square roots cancel out, I get x plus 1. And then, here's the whole reason for using the conjugate. Notice when I multiply the outside, I get 2 square root of x plus 1. When I multiply the inside, I get negative 2 square root of x plus 1. Those add up to 0. That's why we use the conjugate. That's why we change the sign in the middle. It makes the middle two terms cancel out. On my last, I have negative 2 times 2. That's negative 4. Okay, now on bottom, I'm not going to FOIL it out. And we'll see why in just a minute here. Notice my square root started in the top. I multiply by the conjugate. I FOIL out the top, but I'm not going to FOIL out the bottom. I'm going to leave it as x minus 3 times square root of x plus 1 plus 2. Now the reason I didn't multiply the top out is, look what I can do next. This is the limit as x approaches 3 of x minus 3 divided by x minus 3 times square root of x plus 1 plus 2. I really needed this x minus 3 down on the bottom to go away. That was really where I had the problem, because when I plugged 3 in, I got 0 on bottom. So I didn't want to distribute here because I wanted to leave this factor of x minus 3, because I was really hoping I'd have this x minus 3 and then I'd have 1 up on top, which I do. That allows me to reduce. Okay, so that's why I didn't want to FOIL it out. I didn't want to FOIL it out. I wanted to leave that x minus 3 there. I wanted to be able to get rid of it. Alright, well now I think I can go ahead and just plug my number in. So when I plug my number in, I have just 1 on top. 3 plus 1 is 4. Square root of 4 is 2. 2 plus 2 is 4. So there's my answer, 1/4. E is similar in the sense that when I plug 0 in, I get 0 on top and 0 on bottom. The difference is D had square roots up on top, E has square roots down on bottom. But that doesn't really change the technique. The difference is I have to rationalize again, but this time we have to rationalize the denominator. Basically, rationalizing means get rid of the square roots. So I want to get rid of those square roots on bottom, which means I multiply by the conjugate of the bottom. So I'm going to multiply top and bottom by square root of 2 plus x plus 2. Once again, I'm going to FOIL one and not the other. This time I'm going to FOIL the bottom. The bottom was the one that started with the square roots. That was the one that had the problems. The top didn't have a square root in it. It didn't really have a problem to begin with. I'm not going to distribute. I'm just going to leave it alone. So I'm going to leave the top as x square root of 2 plus x plus 2. Down on bottom, again, I multiply these two things. The square root goes away. I get 2 plus x. The outside and the inside reduce each other. That's the whole reason for switching that sign and using the conjugate. Oops, I see I made a mistake. I should have had square root of 2 on both of those, because that one had a square root of 2. Square root of 2 times square root of 2 is negative 2. Alright, again, some really nice things happen. I can simplify the bottom. Do it in 2 steps here, I guess. This becomes limit as x goes to 0 of x square root of 2 plus x plus square root of 2. I forgot my square root there also. Divided by x, because the 2 and the negative 2 add up to 0. I can now reduce. I can reduce the x's. Those are gone. And now I think I can plug in 0. When I plug in 0, I get square root of 2 plus square root of 2. Notice I don't need to write my limit symbol anymore, because I'm actually plugging in the number. 2 squared to 2 looks like my final answer. Okay, F is for you. Very similar to D. Okay. Moving along. Sometimes we have problems that look like this. These are called compound fractions. What we mean by a compound fraction is we have a big fraction, and then within the big fraction we have other fractions. Once again, if I saw this problem on a quiz or a test, I would try to plug in 0. When I try to plug in 0, I would notice I get 1/3 minus 1/3, that's 0. I get 0 on bottom, 0 over 0. I've got to simplify. Okay, probably the easiest way to do these problems is to clear the compound fraction. To clear the compound fraction, you're going to multiply top and bottom by something. You're going to multiply top and bottom by the common denominator. So the denominator of the first fraction is a 3 plus x, and the denominator of the second fraction is a 3. So that's my common denominator. That's what I would multiply by. When I do that, I have to distribute. So this becomes a limit as x goes to 0. When I take 3 plus x times 3 and multiply it by this first fraction, the 3 plus x is reduced. So I'm left with 3. Minus, when I multiply this common denominator by this fraction, I can reduce the 3's, so I'm left with 3 plus x. And then down on bottom, I guess I'll just leave it, x, 3 plus x, 3. Now, once again, some good things should happen now. I should be able to do some pretty simple reductions, and something good should cancel out. Let's see what happens. This is limit as x goes to 0 of 3 minus 3, that's 0, but then I've got to take that minus sign and distribute it through there, so that's minus x over x times 3 plus x times 3. I notice that I have the x on top, the x on bottom. I can reduce those, and that really got rid of my problem. The problem, again, way back from the beginning, is when I tried to plug 0 in, I got 0 on bottom. I now got rid of that. I plug in 0. When I plug in 0, I have negative 1 on top. I have 3 times 3, that's 9 on bottom. H is for you. Okay, now we have two special trig rules here. And the trig rule, I can probably best convince you of this using a graph. I'm going to take sine of x and divide it by x. And I want to take the limit as x goes to 0. Well, again, if I try to take this function and plug 0 in, I would have sine of 0, which is 0. I'd have 0 on bottom, that would be 0. That's 0 over 0. Don't know. But there's really no reduction I can do. Okay, let's take a look at a graph of this function. I'm going to do even better. I'm going to do a zoom trig. So, by looking at the graph, I think you would be pretty convinced that as x goes to 0, sine of x over x is getting close to 1. And there's an actual proof of this in your book if you want to read it. It's listed on page 65. What you need to know is two theorems. One, the limit as x goes to 0, sine x over x equals 1. And then there's another famous trig one, and it involves 1 minus cosine x over x. Again, if I try to plug 0 in here, I would get 0 over 0. Looking at this graph, I think you would be pretty convinced that when x goes to 0, this function is getting close to 0. So those are two famous trig functions that limits that you need to know. Okay? Again, these are in your book on page 65 if you wish to look up the proofs of these. Really, what I want you to be able to do here is I want you to be able to use them. Okay, so looking at number 3. Number 3 almost fits the pattern for rule number 1, but rule number 1 had sine x over x. Unfortunately, we have sine 5x over x. what we need to have happen is we need to have this angle and this denominator match. Once they match, it wouldn't really matter what I had here. If I had 5x over 5x, that would still be the limit 1, because these would be moving at the exact same rate. Alright, so what we need to do is we need to put a 5 right there. Well, of course, the penalty for multiplying by 5 on bottom is I have to multiply by 5 on top. So we do that. We multiply top and bottom by 5. Now we use the fact that this part of the limit is the number 1 by our theorem. So 5 times 1 is 5. Okay, not so bad, I hope. Part B, kind of a similar situation. We have a 3x here, we've got a 4x there. We really need those to be the same. What I would do on this one is I would rewrite this. I would rewrite this as a limit as x goes to 0 of 1/4 times sine of 3x over x. So I kind of just started by taking this 4 here and moving it out, writing it separately. Now I have really pretty much the same problem I had in part A. I need the 3x to be the same on top and bottom. Well, in order to make it the same on top and bottom, I simply multiply. Multiply top and bottom by 3. Now I use the theorem up above, which says this part of the limit goes to 1. So I have 1/4 times 3 times 1. That sounds like 3/4. Okay? Alright, well, as you probably guessed by now, you get to try part C. Part D. Part D uses the other part of the theorem. The other part of the theorem says that this part of this limit right here is 0. So this is 3 times 0. That's 0. That was an easy one. Alright, E is a little bit tricky, but I'm going to leave it up to you. I'm going to let you take a shot at it, see if you can come up with the answer. If you're having trouble, send me an email. We'll take a look at it together. Alright, almost to the end here. We got 4 and 5 to go. 4. Evaluate the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. This is an extremely important thing. What I have just written there for you is the definition of something called the derivative, whatever that is. Well, it's that thing right there. We're going to spend probably the next 2/3 of this course studying derivatives and everything derivatives are good for. So this is probably the most important thing for this course. And truthfully, this is why we study limits. We study limits because limits allow us to define a derivative, and later on we'll see limits allow us to define an integral, whatever integrals are. Okay, so how does this work? Well, this symbol here, f of x plus delta x, means take your function, our function is x squared plus 2x, and wherever you see an x, replace it by x plus delta x. So that's x plus delta x squared plus 2 times x plus delta x. And I'm going to go ahead and I'm going to FOIL this out and combine like terms as much as I can. And you do have to be careful here because the x's and the delta x's are easy to get confused. Alright, so when we FOIL this out, we get x squared plus 2x delta x plus delta x squared plus 2x plus 2 delta x. And I guess there's no like terms, so there's really nothing I can combine. However, now I'm going to work on the whole numerator here. Well, let's just write this out. We will have the limit as delta x goes to 0 of f of x plus delta x. We just figured that out. It's over here. So I'm just going to copy that down again. That's x squared plus 2x delta x plus delta x squared plus 2x plus 2 delta x. And then I have to subtract the original function. big long numerator here, minus the original function is x squared plus 2x, and everything is divided by delta x. Now, as you may have surmised by now, if I were to try to take delta x and plug in 0, I would get 0 on top and 0 on bottom. Certainly I get 0 on bottom. So we need to do some reducing. But notice things reduce pretty well here. I've got an x squared and I've got a minus x squared. Those cancel out. I've got a 2x and then I've got a minus 2x. And this is what should happen. When you do a problem like this, you should be able to reduce the numerator, and everything left in the numerator has to have at least one delta x in it. If you have a term left over after you've reduced that does not have a delta x, then you've made a mistake. The reason it's important to have a delta x everywhere is that you can then factor it out. So, with everything left out on the top, I'm going to factor out a delta x. When I factor out delta x, I'm left with 2x plus delta x plus 2. And then I have delta x on bottom. A wonderful thing happens. Oops, delta x is going to 0, I forgot. A wonderful thing happens. You can reduce the delta x with the delta x, and now you can plug in delta x. When I plug in delta x equals 0, I get 0 right there. I'm left with 2x plus 2. Okay, so do you remember on the very first day of class, I told you something and some of you kind of snickered, thought I was kidding. I told you that calculus is very, very easy. In this whole problem that I just did, all that writing, where was the calculus? The calculus, the only spot where I really did calculus was going from here to there. And notice all I did, I plugged in 0. There's calculus. Calculus is plugging in 0. Now, unfortunately, to get to that point, I had to do 1, 2, 3, 4, 5 steps of algebra. It's the algebra that's hard. That's where you're going to make the mistakes. The calculus itself is as easy as it gets. Plug in 0. I plugged in 0. There it is. Okay, part B. One for you to try. Alright, the last thing we have in this section is something called the squeeze theorem. I'm going to draw you a picture. Here's what the squeeze theorem says in words, and then I'll draw you a picture. The squeeze theorem says if f of x is less than or equal to g of x, and that's less than or equal to h of x, and the limit as x goes to c of f of x equals L, and that's also equal to the limit as x goes to c of h of x, then the limit as h goes to c of g of x is also L. Alright, so what does that say? Well, the easiest way to describe this is in a picture. Basically, we have three functions. We got f, g, and h. And we've got some value x equals c. F is the smallest function. So f is down here, it's wiggling along like so. I don't know what f does. This is f of x. H of x is the biggest function. So h of x is up here. Again, it's squiggling along, comes about like so. And we know that the limit as x approaches c of f of x is L, and the limit as x approaches c of h of x is L. So, I got my f of x function down here, I got my h of x function up here, and they're coming right together at c to have a limit of L. Well, the theorem says g's stuck in the middle. So this is called the squeeze theorem because g is squeezed by f and h. It's also sometimes called the sandwich theorem, where f and h are the bread and g is the stuff in the middle. Alright, well, what has to happen? G's in the middle. G's always in between f of x and h of x. I don't know what g's doing. It's going all crazy here. But when it gets close to c, it's stuck in the middle, so the only option is its limit has to be L also. Alright, so that's what the squeeze theorem says. So here's how you're going to use it. Use the squeeze theorem to evaluate the limit. It wants the limit as x goes to 0 of x sine of 1 over x. Well, this one has some issues. The big issue is when you try to plug 0 in, sine of 1 over 0, 1 over 0 is undefined, sine of undefined is undefined. You can't just take the number 0 and plug it in. So what we're going to do is we're going to squeeze this function. We're going to take x sine of 1 over x, and we're going to squeeze it in between two things. And here's what I'm going to squeeze it in between. X times 1. Now, why can I just say that x sine 1 over x is less than or equal to x times 1? Well, what's the biggest possible value for sine? Sine itself is stuck between 1 and negative 1. So the biggest possible value is 1, so x times this has to be less than x times 1. Conversely, the smallest possible value for sine is negative 1, so I know that this thing has to be bigger than negative 1 times x. And now look what happens. The limit as x approaches 0 of negative x equals 0. The limit as x approaches 0 of positive x equals 0. These are both 0. Since this thing is squeezed in the middle, that one has to be 0 too. So the limit as x goes to 0 of x sine 1 over x has to be 0. Alright, so you have one last problem to do, and that's that one. Okay, so I think I stated this earlier. I'll state it again just to make sure. This is going to be due Monday of next week. I'll talk about this in class. I'll have this handout for you. See you Friday.